Now, let us discuss the torsional pendulum. Assume a rigid object is suspended from a wire attached at its top of a fixed support. And this is a rigid object, and this is a wire. Okay. The twist wire exerts a restoring force, restoring torque on the object that is proportional to its angular position. That is, if you twist the wire by twisting the object, and you will have the restoring torque. Now it is a restoring torque. It means that it is a torque that tries to restore the equilibrium configuration of the system. The equilibrium configuration is the configuration when the object does not twist or the torque on the object is zero. This is similar to the case of the spring, but in the case of the spring, the equilibrium position is a position that the force, the restoring force, is zero. In this case, it is a position, the angular position, that the restoring torque is zero. We can write down the restoring torque as the torque is equal to the minus of the kappa and theta. Here theta is the angle that we twist the wire. Okay, and this kappa is a torsional constant of the support wire. The kappa is a torsional constant of the wire. You can see that the mathematical form of this equation is very similar to the Hooke's law. The minus sign here tells us that the restoring torque will try to twist back to the equilibrium configuration. That is, if you try to move, if you try to rotate this rigid disc in this direction counterclockwise, the restoring torque will try to twist it back to the equilibrium position. So if you define the counterclockwise direction as a positive, so the restoring torque will try to twist it back in the negative direction. Okay, so this is very similar to the spring case. And since we have the torque on the rigid body is equal to the moment of inertia times the angular acceleration, so we have that the kappa, the minus of kappa theta, is equal to the I, the moment of inertia, and the second derivative of theta with respect to time. So if you look at this equation, you can see that this is very similar, and it has the same form as the equation for the spring, the restoring force from the spring. If you replace this with the spring constant, if you replace this with the linear displacement, and if you replace this term I with the mass, you will get the identical equation to the restoring force in the spring. So we can rearrange this equation a little bit to get d square theta by dt square is equal to the minus of the kappa over I theta. Okay. And since the mathematical form of this equation is very similar to the spring case, we can expect the same form of the solution of this equation for theta. So we must have that theta t is equal to the theta max, the maximum value of the angle, cos omega t plus phi. Okay. Sorry. The value of omega can be obtained in a very similar way to the spring case. And if you look at this equation, you can see that this term, if you compare with the spring case, this term will give you the angular frequency. So we can write down that the angular frequency omega is equal to the square root of the kappa over I. Okay, this is similar to the expression in the spring case that omega is equal to the square root of k over m. And from this relation, we have that the period of the oscillation is equal to the 2 pi of the square root of I over k. Okay. So the object will oscillate back and forth with the angular frequency of this value, and the period of the oscillation is equal to this value of t. Note that in this calculation there is no need to assume the small angle approximation, because in this equation you can use it directly without any approximation. It's unlike in the case of the pendulum or the physical pendulum.